Hey guys, welcome to another lesson. So hope you've been enjoying the lessons previously. Today we're going to start Trig. So I've got a few videos on 3D Trig. You can go look at that. It's in the previous videos recorded. Today we're going to talk about transformation or the auxiliary method, some schools call it. And next lesson, I want to do T results. Now, both of those topics in some textbooks fall under a separate trig topic called trigonometric equations, sort of separated from the normal trig topic. That's a bit weird because I think it's fair to say with transformation and T results, you can always have different types of questions not relating to trig equations. Not sure why they sort of split it out. Maybe they thought the trig topic was so big, they wanted to sort of break it apart. And that's fair because I always say this with my students, especially in year 11, pardon me, extension 1, the syllabus in extension 1, trig by far and away is the hardest topic. It's got the most content. It's very heavy, right? So if you know, for my students, I basically put all the formulae in extension 1, year 11, all on a double-sided A4. It's massive, right? So if someone tells you it's calculus that's the hardest, or functions, yeah, they're decent, but trig far and away hardest topic, and some consider it to be potentially the hardest topic in extension 1, 3 unit. And also there's a good point. This video and next lessons video is extension 1, not advanced, out of syllabus for advanced. Extension 1, extension 2, obviously this is like known knowledge, so that's in play as well. So today, transformation. Some schools call this the auxiliary method, right? I like calling it transformation because that is exactly what the process is and looks like. Auxiliary doesn't give anything away about what you're trying to do. So the reliance on known knowledge is key to this. So I'm just going to say recall. The two compound angles that you learned, right? The sum and difference for sine looks like this. Now, if you did this wrong, you go sine brackets a plus b and you expand it to sine a plus sine b. That's not true. We know that sine a cos b plus sine, let me put the cos on first. Cos a sine b, that's the proper expansion. And just to be clear there, as a little shortcut, if this was a minus, this would be a minus as well. Yeah, I combine it for my students so you don't have to write it twice. And similarly, cos compound angle changes slightly. Instead of sine cos, it's cos cos. And importantly, if that's a plus, this is a minus, and this is sine sine, right? And of course, if this was a minus, this will be a plus as well. So that's a good start. Yeah. That is required for the transformation process because all you're trying to do, right, in a nutshell, is for transformation, you're going to transform expressions that have, let's say, a sine x plus b cos x, right? So if you ever have a trig equation where there's sine and cos ratios in the same expression, you're in trouble, right? I say you're in trouble, you need to do something. It's very hard to solve an equation with sine and cos in there. Yeah. So with if you were to do angles of any magnitude or all stations central with this, very hard, right? If that equals to a number now, a and b, they're a constant. What we need to do, right? We need to transform this expression over here, a sine cos, into an expression that only has one ratio, sine or cos, right? So we're going to transform this into r. Now, the rule of thumb I always say to my students, if the question doesn't say, sometimes the question tells you, but if the question doesn't say and you start with sine, right? Start with sine, see how sine there is at the start, use the sine compound, right? Plus alpha, yeah? So you can see by transforming, right? And I'll use maybe an arrow here, right? A sine plus cos into this, you can then use r sine a plus alpha to solve the remaining question. The only thing you need to consider here is that there's two variables, right? There's r and alpha for you to find. Yeah. So in this case, once you transform, you can say to yourself, or you can write down as part of your theory, need to find r and alpha. Yeah, alpha's an angle, R's or R's a number, right, constant. So that's important for you to sort of see that that's the process we're going to do. We're going to solve trig equations and graph trig graphs in 2 steps. 1, we're going to transform. 2, we're going to take that on and then finish the question off, right? And just to be clear, so if I had, another expression, let's do cos first, right? With a plus there, just to demonstrate something. You would consider then all else not given. If they don't give you what they want, you can use cos because you started with cos. But the key thing there is if that's a plus, we know the plus version of the formula uses the negative or the minus compound for cos, right? That is a transformation process we're going to use. Yeah, I've got 3 past papers prepared, 3 past paper questions prepared just to illustrate these points. Let's hit it off. So first one's Balcom Hills 2009. So you can go through extension 1 past papers. These questions, I'd be very surprised throughout the year, any students year 12, year 12 history, that they won't see one of these. You definitely will see one of these. And look at the marks, right? 4 marks. We're talking an extension 1 paper, which is 70 out of 70 marks in total. 4 marks, that's probably like 6%, 7%, right? So decent. Yeah? Probably more 6%. So look at the question. Express this in this form, right? So they gave you the form that they want. Instead of R, they use A, and that's absolutely fine. But what's key is that, before I had A sine plus B cos. In this case, right, A is 1 and B is √3, right? And then we transform. Can you see it's always in 2 steps? Part 1, transform. Part 2, use it. In this case, solve. Sometimes it's a sketch. Sometimes it's to find a maximum, et cetera, right? Let's do it. Oh, and hence solve that, right? So we're going to use it. Perfect. So you can't get any more classical than this question, right? This 4 marker is a classic. So we want this to equal to A sine x plus alpha. Now, a better question would tell you that alpha is between 0 and pi on 2 or 90 degrees, right? But in this question, let's just assume that it is. Right? So what do? So I can see, right? It's going to make this guy 1 and this guy √3 if that's okay, right? Now, step 1, I'm going to apply compound angles to this guy. Yeah, sine A plus B, right? In my formula before. So I'm going to just basically expand that to sine. We'll put brackets in. Put better brackets. Sine x plus, sine x cos alpha plus cos x sine alpha, right? Just like I did before. And then I'm going to use rainbows to gently expand that. Sorry, I want a different color because I'm using blue for something else. Yep. So then I get A sine x. Can I ask a favor? I always ask this from the students. Can I put the cos alpha first? It's just easier to demonstrate a point, right? So when I expand, so sine x plus A. Once again, let me reverse your sine alpha cos x. Right, so therefore, sine x plus cos x with a 1 over here and a √3 over here equals to this. Now, this is a key point, all right? We have an expression right now that sine x is on both sides, which makes sense then that the number in front and the expression in front are equal, right? So in this case, therefore, I can say A cos alpha equals to 1. And if I made cos alpha the subject, divide the A over, I get that expression. Similarly, this expression has a cos x there, that has a cos x there. If I compare both sides then, √3, the number in front of cos x should equal to A sine alpha, the number in front of that, right? They should be equal. So in this case, A sine alpha should equal to √3, which means if I made sine alpha the subject, I get this. Now, at this point, there's 2 ways to do this. Sorry, there's a few ways to do this. Some teachers like Pythagoras, and then they use a bit of trick. I like to always get my students, so once you get these two, the blue and the pink here, I always get my students to convert that into a right angle triangle. Yeah, just to visualize it, because with this sine alpha, let this guy be alpha. Sine alpha is opposite on hypotenuse, cos alpha is adjacent on hypotenuse. And from this triangle, you got everything, right? You got by Pythagoras. You get that, and you get therefore A is 2, right? Nice numbers, yeah. And also you can use a tan ratio there to go opposite on adjacent, which is a nice exact value there to be, what's that, 60 degrees, so pi on 3. Once you got alpha and got A, in this case, that's all they need, right? Because if you look at the question in the form, that what really was missing is the value of A and the value of alpha. So sub that back in and you transformed, right? You have transformed this expression. You go, therefore, sine x plus root 3 cos x has been transformed into what? Into A, which is 2, sine x plus alpha, which is pi on 3. That is, the crux of what we're trying to do here. By transforming an expression, right? So let me just box this. By transforming an expression that had sine x and cos x into an expression that has sine only, we can now do something with it. So auxiliary method transformation, done. Now, let's use it. What's my second question? My second question is, can I please solve the expression equal to 1? Now, just by looking at it, it's very hard to solve an equation with sine and cos equal to 1. All stations central doesn't allow that, right? ASTC only allows one ratio, sine, cos, or tan, equal to a constant, right? And then I can go forward. So what did I do? In part 1, I have transformed this expression, right? I have transformed this expression into an expression that has 2 sine x plus alpha into an expression that only has sine, right? Only has sine, and that is key, right? Equal to 1. Because once I have this, I can just apply all stations central to that, where I go divide the 2 over. Now, different schools have different ways of doing ASTC. I always say to my students, sine is positive in the first and second quadrants, in which case I'd ask my students always to write down the first and the second, where it's theta and 180 minus theta. In this case, right, the theta is x plus alpha. So I go, therefore, x plus alpha. If I shift sign that to get my equivalent first quadrant positive value, that is 30 degrees or pi on 6. Yeah, actually, what I haven't done, and it's silly of me, I haven't put alpha in, right? Oops. Yeah, I need to get alpha in. So can you put in pi on, was it pi on 3? Pi on 3. And pi on 3 here. Yeah. Just make sure these numbers are right. Perfect. Right. Now, we know with ASTC, when I sub this guy in here, I get pi on 6, but I also need to sub in here now. In terms of pi, that's pi. So pi minus that would be 5 pi on 6 as well. So I get 2 answers, right? Almost there. So once you get there, you've basically transformed, solved, and now to make x a subject, I have to throw this guy over the fence and this guy over the fence. I've got to minus both of them, both of my solutions here, by pi on 3. So that guy minus pi on 3 is negative pi on 3, oh, pi on 6. This guy's a pi on 2. Yep, perfect. You can do it on your calculator. Now, look at the domain. You want between 0 and pi on, and 2 pi. Almost there. This is almost your answer, but this answer here is negative. So I'm just going to add 2 pi to make it come back within the domain that I want. So therefore, my final answer will be this guy plus 2 pi. Was that 11? Pi on 6 and pi on 2. Final 2 answers. So, the whole purpose of transformation is to transform an expression with sine and coses to something that only has one of them. In this case, only has sine, with the purpose, final purpose of then solving an equation, in this case, using all stations central. Yeah. Let's look at another one. Now, for the next one, from North Sydney Boys in 2017, it was very simple, but can I ask a favor? All right, let's pretend that there were two parts to this question. Let's go, this is part A. Yeah, and I'm going to just subtly add part B where I go sketch y equal to sine x plus cos x, yeah, for the same domain, let's say. And I reckon I'll give this 2 marks, right? 5 marker. Yeah. So I like the first question, firstly, because it's got no direction, right? It doesn't say use transformation, use T results, which is next week. Let's use transformation because that's, we'll save T results from this. This is a really good candidate. And I think I will choose something like this next lesson to compare the two methods, right? Maybe I'll put a minus in between. So part A. So if you're given sine x plus cos x, right? I want you to ignore the 1 for now. Just look at the sine x plus cos x because I need to transform that, right? So right now, it's like there's an invisible 1 there and there's an invisible 1 there, right? Now, remember what I said before. If it's sine x, I would consider using the compound expression for sine. Yeah, like that. And then just like before, I'm going to expand this guy. Sine x, cos alpha plus cos x, sine alpha. And guys, rainbows that. And then can you switch the order of the x and the alpha to be r cos alpha sine x plus r sine alpha cos x, right? So therefore, that's right. I can do this in PowerPoint. Yes. I wouldn't miss that when all my classes resume face-to-face. Now, once you do that, we know there's a sine x expression there and a sine x expression there, which means, guys, the number or the constant in this case in front should equate to that expression there. So we do exactly what we did before. Therefore, r cos alpha equals to 1. And then cos alpha equals to 1 on r, tick. That's 1/2 of the information I need for the right angle triangle. So similarly, cos x is there, there's an expression for cos x there. We equate the 1 with the expression for r sine alpha, right? So r sine alpha equals to 1, make sine alpha the subject, 1 on r, tick. That's enough information right now for me to go, therefore, in my right angle triangle, if I call this alpha, sine alpha is opposite hypotenuse, cos alpha adjacent on hypotenuse. By the way, you don't need this, right? Some teachers won't do this, but I find the right angle triangle really useful, especially for other topics like inverse trig, right? It's a really good way of practicing the drawing of a right angle triangle and getting your trig information. I like it a lot. Guys, Pythagoras. Yeah, I mean, from there, therefore, r equals to √2. And then using your tan ratio, that's 1 on 1. We know that that's 45 degrees, which is pi on 4, guys, all right? Sub that back in to the original statement we did here. So therefore, right, we've transformed sine x plus cos x, with the ones in front, to an expression that is r sine x plus pi on 4. Great. Now, once you've done this transformation, what's the question saying? I want you to solve sine x plus cos x equals to 1, right? So now, how much space do I have? None. Okay, let's come up here. So I can go, therefore, sine x plus cos x is 1. I have transformed this expression to √2 sine x plus pi on 4. And here we go again. That is an ASTC question, right? That I can now do because I only have one ratio, not sine and cos, just sine, right? So let's see this. Divide the √2 down. So make that the subject. 1 over √2, guys. ASTC that, please. So just like before, sine is positive in the first and second quadrants. We know in the first quadrant, it's theta. In the second quadrant, 180 minus theta. I always write 180 even though we're doing radians because then I converted pi after. So this is the expression I want, right? That's like my theta. So therefore, x plus pi on 4 equals 2. If you inverse sine that, that is also pi on 4. And then 180. So sub that into there. That's pi on 4. Sub that into there with a pi there. Pi minus that 3 pi on 4. What do I need to do? I need to make x the subject. So I would minus that guy over to both of those. So therefore, pi on 4 minus pi on 4 is 0. And just remember, whenever it's 0, because is my domain between 0 and 2 pi inclusive. So if my answer is 0, it also needs to be 2 pi as well automatically. And then 3 pi on 4 minus pi on 4 would be pi on 2. You'll see for this question, if I did this exact question for next week, that pi on 2 might be problematic for T results, but it's a special case, guys. But right now, transformation for 3 marks, North Sydney boys. Is that okay? Yeah, because let me take the opportunity now to do the next part, which let's see if I can do a bit of a rejig because I need a little bit of space. So let me just move this over here. Perfect. I just put a space on the right. I need to sketch this. So this is why I don't think this topic should fall under a banner called Trigonometric Equations, because it's not always equations that I can apply this to. I'm going to apply it to sketching and functions, right? So check this out. Now, there's 2 ways to do this. One bad, long way, and one smarter way, right? So if I was to sketch y equals sine x plus cos x, right? For the domain of 0 less than x less than 2 pi, right? Now, theoretically, don't do this, please, right? I can go, well, sine x looks like this, right? I know that cos x looks like that. I can add the ordinates, which is a technique they teach you now in the functions topic, right? Where you add the y values to stack it up to get a combined graph. You can do that, right? Absolutely perfect. Takes ages, right? Takes ages, and you're doing points, and it's a bit annoying. So let us use a different way. We're not only going to use transformation on the algebra with sine and cos. We're going to use transformation of functions. I'll show you what I mean. So we know that this expression has transformed into y equal to root 2 sine x plus pi on 4. Now we know, right? It's very hard to sketch a graph with sine and cos, but with sine, we can do it, right? We're basically starting with our normal sine curve and doing a few transformations. Now, in the new syllabus, I keep referring to new syllabus, so I should just say in the syllabus, this expression has 2 transformations to the sine curve, right? First one, it's got something that multiplies out sine. They now call that vertical dilation. Yeah. So if it's root 2, it basically stretches. Now, we know in trig graphs, vertical dilation is also known as amplitude, right? The height of the wavelength from the center. Yeah. In this case here, if I'm adding a constant inside where x is, that moves the graph left and right. That is a horizontal translation. Now, there's a special term for that, isn't there? This is horizontal translation, which is otherwise known as phasing, right? Or phases. Yeah. So it's got a phase of the sine curve. So what do I need to do? I need to stretch the graph vertically a bit for root 2 by root 2 because of dilation. And I need to, guys, if it's plus, it's a horizontal dilation to the left, right? By pi on 4. So can I ask a favor? Whenever you try to sketch this, right? I always say to my students, always do the horizontal the phasing, the shifting left and right last. And I'll show you what I mean, right? So while we're here, while I'm at it, can I just take a bit of time and do a nice number plane, right? Because I got PowerPoint up, I can do this. It just looks nice, all right? Just so I can have something else like that. go 6, 0. Perfect. I'm gonna select both of these. Line centers. Perfect. All right. Love the PowerPoint. All right, there we go. No, I don't want to center there. I want it to be like 0. Yeah. Perfect. Now we know that. Let me draw a fake answer here, right? Between 0 to pi, and there's pi here. Yeah. Now we know that normal sine curves go from 0 to 1, something that looks like that, right? Yeah. Don't want. So I'm going to draw two graphs. Firstly, I'm going to draw a graph in green. That's not my final answer, but it has an amplitude or a vertical dilation of √2, right? So it doesn't have that phasing, right? The plus pi on 4. And then I will do my final answer in pink, right? I'll do my final answer in pink, but it's really smart to look at the green first and then phase it thereafter. So pi on 4 on your calculator is approximately 1.414. So the green basically goes up to about there, √2, and down here, negative √2, right? Same. The period hasn't changed, so it's still starting from 0, and it ends at 2 pi, and it sort of crosses over in here, right? And the highest point it goes to at pi on 2 is here. Actually, it's worthwhile labeling the pi on 2. You'll see later why. It's a good reference point at 3 pi on 2, of course. And the grid so goes to the maximum amplitude positive there and negative amplitude there. So let's do it. Let's see if I can actually sketch this. Yeah. Perfect. Yeah. So I'll stop at 0 to 2 pi because that's what my domain was, right? Now, just be clear, this graph here, maybe I'll do it like this. This graph here was y equals to √2 without the phasing. That's not my final answer. How do you phase this, right? How do you shift this pi on 4 or 45 degrees to the left? This is what you do. Piece of cake. I mean, what is 45 degrees? If from 0 to pi on 2 was 90, then half of that, right, would be 45 degrees. So basically, I'm going to shift this green graph half a unit to the left, right, for half of these units. So this is what I'm going to do, right, theoretically. So if I was to make a copy of this, right, and stack it right on top, theoretically, I'm just going to move it like that over. Now, another way to do it is if you have the green without PowerPoint, if you have paper, you just literally take all the key points, this top here, move it 45 degrees or half a unit that way, this one half a unit this way, this one half a unit this way, this one half a unit this way, and just plot that for now, right? Yeah, just plot that for now. Because then the only thing you need to find out now is where's the y value? Oh, so where's the y-intercept? Because that's going to be the same value that you're going to end the graph with, right? So off to the side, you know, the y-intercept, right? We know that when x equals to 0, sub it into y equals to √2 sine 0 plus pi on 4. Guys, I know sine pi on 4 is 1 over √2, that equals to 1. So the y value is exactly 1, right? So it sort of begins at 1, goes up, and then dips down. And this means that when it finally finishes, it should finish on the 1 as well. And that's my graph. That's my phased graph. So, oops, 2 sine x plus pi on 4. How's that? So, maybe this is a 3 marks, to be honest. Maybe not 2 marks. I underplayed it, but I thought I'd throw that in there just to show you that, with transformation, sometimes the question isn't solve this equation. Sometimes it's sketch. And sometimes you might see the question that says, can you please find the maximum value of this? The best way to find maximum value is to picture it as a graph. There's a maximum value, √2. What's the smallest value? Negative √2. You can see it, right? So sometimes they ask you to transform part 1, and then part 2 can be either solve this equation, can be sketch the graph, can be find the maximum value of it, and you can use the graph to sort of help you do it. Guys, you know what? I'm going to leave it there. I think that's a good demonstration of this. Obviously, some of the harder questions with this can be, the numbers for alpha or r are not exact, really ugly, and that's fine. Sometimes you'll see that instead of sine x plus cos x, it's like sine 3x plus cos 3x. So there's that extra element that when you solve for ASTC, part A doesn't change, transformation part doesn't change when it's 3x and sine 3x, cos 3x. It's the solving ASTC that you got to divide all your angles by 3 and then find sort of 3 pairs of it, etc. Right? So there's a few variations there. Keep those in mind, but that's how you use the transformation auxiliary method. Next lesson, we will contrast this with the T results, and I'll show you an example where I'm solving a question side by side. Hope you liked the video, guys. If you haven't already done so, please give it a like, tell your friends. Helps with the search engine on this. So yeah, I'll see you guys in the next video.